All right. So first of all, so Nathan, I saw there are several people here in the classroom. Hello. So first of all, let me recap the previous lecture regarding Chris' question, right? Regarding why we went through the route of using the partial sums of the exponential random variables to prove the sample quantile. So just as a recap, the logic of deriving sample quantile is that we first prove that if we have the y1 to yn plus 1 as IID, right, exponential 1. And also we have u1 to un as IID uniform 0 to 1. We have these two sets of IID random variables. And then what we did is to define the partial sums Si as the summation j from 1 to I as j. In other words, it's just Si taking the sum up to Si. So with those, Yi taking the sum to Yi, like that. So with this partial sum definition, an interesting lemma we first prove is that we can show that for S1 over Sn plus 1 up to Sn over Sn plus 1, conditioning Sn plus 1. So this vector has a joint distribution, same joint distribution as U1, the order statistics to UN. So this is the beginning. So back to Chris' question, why we use exponential random variables is because this relationship only holds when we have y1 to yn plus 1 following exponential 1. If you change it to another distribution, then we don't have this relationship. And why is this relationship crucial? The reason is that we have our central limit theorem as our tool for deriving the asymptotic distributions for the SIs if I and n both go to infinity at a ratio. So the setting is that we have I goes to infinity, n goes to infinity, but we actually require this root n times 1 over, root m times 1 over n minus p. This will go down to 0. So in other words, I over n is convergent to a proportion p with p between 0 and 1. So the p is the quantile we want to look for. So that's why here, as I is also going to infinity, our central limit theorem would apply to Si and also would apply to Sn minus Si. So that's what we did in the last time. And so basically, from this result and the central limit theorem, we are able to derive the joint asymptotic distribution of, so based on, let me say, based on this result 1 and central limit theorem, what gave us was the joint asymptotic distribution of this thing, root m, if you recall, of this u order I, u order j. Okay, so minus p and q. And this will converge in law to some normal distribution, two-dimensional normal distribution with mean vector 0. And also the covariance matrix is p times 1 minus p, p times 1 minus q, p times 1 minus q, and q times 1 minus q. And this is subject to the constraint that, okay, we have 0 less than p less than q less than 1. So p and q are two values between 0 and 1 with an order, p is less than q. And we are interested in using the, ui as the sample quantile, sample p quantile for a uniform sample. and UQ as the qth sample quantile for the uniform sample. So that's why we actually have root n I over n minus p goes down to 0, root n times j over n minus q goes down to 0. So therefore, you know that I over n and j over n are approximating p and q respectively. So therefore, ui, as I said, uj is the pth and qth sample quantiles of this sample u1 to un. So this result is our starting point. So based on what we have for central limit theorem, and through this interesting relationship between the ratio of partial sum and in the exponential one sample and the order statistic, which corresponds to sample quantile in the uniform sample, we make the connection. So we have this important result for sample quantiles of a uniform sample. So does this make sense to everyone? And through the process to get to here, we need to use the delta method. So we can go from the central limit theorem for the joint distribution. Basically, we need a joint distribution of Si, Sj minus Si, and Sm plus 1 minus Sj. So we need those three things, joint distribution, asymptotic distribution. Then we apply the delta method to convert that to Si over Sm plus 1 and Sj over Sm plus 1. So then we can have this ui uj with the same distribution lemma. Okay, so Chris, does that answer your question?
Yeah, thank you.
Okay, thank you. And then finally, we go from this uniform sample to the general case. So the general case is that, so let's say that this important result, we call it our result 2, okay? From the first result in the central limit theorem, we go to result 2. Then what we can have for our third result is that, let's say we have x1 to xm following IID some CDF f, okay? F is the CDF. And then what we can say is that for the sample quantile of this sample, okay, we link it to the corresponding quantile in the uniform sample. Sorry, yeah, it's right here, based on the inverse of the CDF. So what we can say is that if we have the, we denote it as the xj, if we denote them correspondingly as the pth and qth sample quantile of x1 to xn. So you can think of this I is the same I here, j as the same j here. Basically, we need I over n close to p, converges to p, j over n converges to q. So with this, then an important result we have is that xi, xj would have the same distribution as f inverse ui, f inverse uj. Okay, the reason is that we know we can go from this uniform distribution through this F inverse transformation to the F distribution. So we are utilizing this result. So therefore, to obtain the central limit theorem, so from 2, this result, from this to this asymptotic result for the uniform sample quantiles, we can get the asymptotic results for this general distribution F sample quantiles. So we could have root n times this xi, okay, xj minus pq will convergent law to still zero mean normal distribution. But now with the delta method, right? The delta method is going to be applied based on this F inverse transformation. So we are going to map the distribution from this asymptotic normality of this through the delta method of this F inverse transformation to here. So we can show that basically by calculus, what's the derivative of an inverse function. So we can show that this becomes just like, oh, sorry, I should change this, my bad, xp xq. So here in uniform distribution, P and Q are just, let me put it here, P and Q, they are just the P and Q's population quantiles of the uniform 0 to 1. So that's just a very nice property of uniform distribution. And here, when we go to this general distribution, we would denote this XP, okay, XQ. These are the P's and Q's population quantiles of this F distribution, okay? So correspondingly, you would have basically XP as F inverse P. Okay, we can write the same thing, XQ as F inverse Q. So everything is connected. So that's why delta method will give us this result from the result 2. And let's call this result 3. And that's our final result. So by delta method, we would change the corresponding covariance matrix. And it turns out to be just a very nice form. So we just scale it, P times 1 minus P, scale it at the density function, which is the derivative of the CDF function. The density evaluated at the population quantile XP squared. And for the covariance is P times 1 minus Q, FXP times FXQ, okay? And similarly, here's the same. I'm just copying it, XP, FXQ. Finally, this one is Q times 1 minus Q. F density at the Q's population quantile XQ squared. Okay, that's it. So we're saying that essentially to estimate the estimate the population quantile, say P quantile, then it will actually, this variance, let's look at the first term, P times 1 minus P divided by density at XP squared. This variance will actually decrease if the density at the P population quantile increases. What does that mean? It means that when there's a larger density, then we are likely to have more data points observed around this quantile in our sample, around this population quantile in our sample. So with more data points around this population quantile, we can estimate this population quantile with better accuracy. So that's the intuition behind why we have this density here. And also you can easily see that the uniform case right here is just a special case, because for the uniform distribution, the density is 1 in the interval between 0 to 1. So all the denominators will become equal to 1. So that's why it's a reduced form. Okay, so that's all I want to say for clarifying the result, which we quickly went to last time. So do we have questions before we show you 2 examples? Okay, so some details are in the notes, so you can check the notes to fill in the details here. All right, so let's see 2 examples for applying this result. The first example is about sample median. And And let's look at the simple case where our sample is from the normal distribution. So let's say that our x1 to xn are IID from this normal distribution with mean mu and variance sigma squared. Okay, so what's the median? The sample median is defined based on our definition as the order, which is the ceiling of n divided by 2. So if this happens to be an integer, we take the integer. If it's not an integer, we just round it up to get a ceiling integer. So that's our sample median. And what's the population median? This should be obvious to us, right? For a normal distribution, which is symmetric, the population median is just mu. So what's the distribution of the sample median around the population median? Let's directly apply this result. So to get this result, now we know xp. So here p is 1/2, right? It's median. So xp, we know it's mu. Then what's fxp? What's the density value of this distribution at the median? So that's where our density has the maximum. And we actually know that f mu is simply 1/√2 pi times sigma. The reason is that that exponential term becomes 1. Since inside exponential, the power equals 0. So exponential term becomes 1. So that's the density left with us. So we are going to just do a plug-in of these things into the formula. So we would have √m times this median, sample median, minus population median, convergent law to a normal distribution with mean 0. And we're going to need just this one diagonal term here, and that's 1/2 times 1 minus 1/2, right? And inside and in the denominator, it's the square root of the density. So it's 1/√2 pi sigma squared. Okay, so simplifying it, we can get the variance as just pi sigma squared divided by 2. All right, so how does this distribution look if we compare it to the asymptotic distribution of the sample mean, which we can obtain by central limit theorem? Let's compare it. So we call that xn bar, right? The average minus mu, and by the CLT, we know it's 0 mean variance sigma squared. So if we compare these two, which one is bigger? So it's basically comparing pi over 2 versus 1. And we know pi over 2 is bigger than 1. So comparing these two things, we can say under this normal distribution, okay, we have this sample median with bigger asymptotic variance. So in other words, we say xn bar is more, we often say, asymptotically efficient than the sample median. And more efficient for what? For estimating mu. So the result just tells us that if you know your sample comes from a normal distribution, then using the sample mean instead of the sample median to estimate the mu parameter is asymptotically more efficient. So we would choose sample mean as the estimator instead of sample median. But sample median has some other advantages because it's very robust to outliers. So by outliers, in our case, it means that your sample may not be purely from the normal distribution. Instead, you may have some other data points that just got mixed in. So in that case, sample median would be less affected by the existence of outliers. But here, this result is not really touching that issue. The reason is we are only thinking about this ideal case where your sample, your observations, your data points are all IID from the normal distribution. So in this case, sample median's advantage is not obvious. Okay, so that's the first example. And now let's move on to the second example. It's a very interesting distribution that doesn't have moments. So it's called Cauchy distribution. The Cauchy distribution still has a center or location parameter mu and a scale parameter sigma, similar to our Gaussian or normal distribution. But the Cauchy distribution doesn't have moments by design. So if you take the density function, let me just write it. For the density function of value x, it takes the form 1 over pi sigma times 1 over 1 plus this interesting term, x minus mu over sigma, just like subtracting the center divided by the scale square. Okay, and here the x can be any real values. So, in this case, if you look at it, right, interestingly, if you just want to simply take the expectation of random variable following Cauchy, then you would do integration x times this dx, but you will not actually have a finite integral. So that's why Cauchy distribution doesn't have finite moments. So we cannot talk about its mean, its variance, etc. But we can talk about its quantiles, population quantiles. So at the population level, we would have the first quartile. By our notation, we denote by x 1/4 quarter, right? The first quartile, and for the Cauchy distribution has a very simple form. It's just mu minus sigma. And for the median, x 1/2, let me write this way, it's just mu, same as the normal distribution. And for the third quartile, 3/4, it's symmetric, mu plus sigma. So therefore, if we want to estimate the sigma, we cannot go from the route of using the sample variance to estimate sigma square as the variance, just as we do for normal distribution. The reason is Cauchy distribution doesn't have a variance, population variance, which cannot be related to, so that's why we cannot relate the sigma to some variance term. But we can use this result, the population quartiles, to relate sigma. So in other words, you can easily see that sigma can be written as the third quartile minus the first quartile divided by 2. So we can give it a name. It's called semi-interquartile range, which means that so the interquartile range is from x 1/4 to x 3/4. That's the interval. That's what we call the interquartile range. And half of it is what we call sigma. So that's why we can define sigma in this way. So therefore, to estimate sigma, a very natural thinking is to replace the population quartiles here by the sample quartiles. Then that will be a natural estimator, right? So in order to do that, we are going to consider the sample quantiles, which is basically from our sample x1, x2, xm from this Cauchy distribution. Let me just write it this way. If we have this IID from Cauchy mu sigma, then the first sample quartile would be n times 1/4 ceiling. And we also need the third sample quartile, n times 3/4 ceiling. We need those two of those. And then what if we take the difference, this minus this divided by 2? That could be an estimator of sigma. And we want to know its efficiency. What's its asymptotic distribution? So to do that, we are going to directly apply our result 3 for that purpose. So by 3, let's just do the direct application. We can easily show that basically root n times this x, n times 1/4, the first quartile, n times 3/4, the third quartile, minus their corresponding population counterparts, mu minus sigma, mu plus sigma, okay, converging in law to that normal distribution. In the covariance matrix, so we can show that by some simplification, it will be equal to 3/4, 1/4, 1/4, 3/4 times constant pi square sigma square. So that's from the denominator, the density square. Okay, so with this, then you see what's left is just to do one step of delta method to go from this joint distribution to the difference of this minus this over 2. So we can show that using that operation by delta method, we would have our estimator okay over 2 minus the parameter of interest sigma converging in law to normal 0 mean, and the final asymptotic variance is pi square sigma square over 4. So therefore, you see one case where we can use sample quantiles to help us construct an estimator for this parameter sigma, even in the case when we don't have moments. Because when we use the sample quantiles to construct estimators, we don't need sample moments, right? So you see, compared to sample moments, what's the nature of it? It's actually some sort of average of my n data points subject to some transformation, right? If I take x1 plus xn plus 2xn over n, that's my sample average, sample mean. But if we look at the sample quantiles, I'm not doing that sort of averaging. I'm just doing ordering, sorting. So I sort my observations from the smallest to largest, and I pick the corresponding order as my statistic. Okay. So that's all I want to say about sample quantiles. Do we have questions before we move on to our next topic? So I would say that compared to our previous results, the sample quantile and the previous one, the extreme order statistics, they are kind of unique, right? Because we are no longer looking at the averages. But still, the link we made with the averaging results was this important result we started with. So the sum of exponential random variables can be linked to uniform random variables, order statistics, which is very interesting. All right, so after this part, now our next topic will become more general. So we're not going to talk about a specific statistic, but we're going to unify our discussion so far into a general framework. And what we call that use statistics. Okay, so that's our next topic. And here the U stands for unbiased. And we will see very soon why we have this interesting property. Okay, so to define that, we first need to introduce a concept called statistical functional. Okay. So what do we mean by a statistical functional? So here, to be very specific, the statistical functional we talk here will actually map from a CDF function to a parameter. So that's why the argument of a functional is itself a function. And here it is the CDF function. So let me just show you some example. So first of all, and let me give you the notation first. So it's called this TF. And this T is what we call the functional, and the F is the CDF. So let's first look at some examples to make it concrete. So first, we can say that the TF could be F evaluated as some constant number C. So what does that mean? It means that I'm evaluating my CDF at this value C, and if I have some Y random variable following F as its distribution, then this FC is basically the probability that Y is less or equal than C by the definition of CDF. So therefore, you see this functional T, this statistical functional T evaluating at F, what it does is to extract the left tail probability of F to the left of C. Okay, so this T basically what it does is that it would actually, what it does is to obtain the left tail probability of F at C. So that's the meaning. So given supplying T with any CDF, any distribution, we will output a left tail probability. That's the first example. The second example, it could be that given F as a distribution and input into the functional F, into the functional T, sorry, it could output the population quantile for this F. So it could give me F inverse P. And here for P, let's say less than 1, greater than 0, right? So if that's the case, then if this TF, what it does is to obtain the Pth quantile, population quantile of F, of the CDF. That's the second example. So still, it actually gave us an output, some property of this distribution F. As a third example, which we see most often, is that given this F, how about I want to know the expectation of this F, right? So in this case, I can write it as this expectation of Y, for which Y, this means that Y follows the F distribution. So I want to take the expectation. So this will be obtain the expectation of Y following F, right? Or we could also have TF defined as the variance of Y if Y follows F. So similar argument, variance. So I can name other examples. For example, here I'm talking about just the tail probabilities, the quantiles, which include median as a special case, the expectation, the variance. I can go to higher order moments like the kurtosis, right? The skewness, those kind of things. But just let you know that for all the properties or parameters we can extract from a distribution CDF, we can define it as a statistical functional. So this perspective will open a big door for us. Why is that? If you think about the parameter as a statistical functional and you want to estimate it, okay, so let's say parameter of interest. Okay, so the parameter of interest of f can be written as theta TF. If we have this, then to estimate this parameter, a very naive way of thinking is to do plug-in. Then we can have parameter estimate. We write as theta hat m from a sample of size m. We can just say, how about we write TF and hat, where the F and hat is the empirical CDF of my sample x1 to xm. Let's say they are IID following F. So with this, you see, I can naturally have a parameter estimate for any parameter that can be written as a statistical functional. And that's why I'm saying we are trying to unify our parameter estimation problem here. Okay, does it make sense to everyone? So replacing the population CDF by the empirical CDF from a sample.
How is the statistical functional different from just a statistic?
Okay, so yes, if you think about we do the plugin here, right? This theta and hat is a statistic. So statistic is basically an operation on your sample, on your x1 to xn, right? You try to summarize them into a number, and we call that a statistic. While statistical functional is different in nature because what it takes is a map. So functional as function is a map. But here, the domain, okay, its domain for functional is a space of functions. While, when we talk about a function, we think about its domain as a space of vectors. So that's usually the case. So here it's a more abstract form of function. So in a functional, your input is a function and your output is some number. So here, only when we apply this functional to an empirical CDF, you can say the output is a statistic. But if you have the functional evaluated at a CDF, a true CDF distribution, then the output is a parameter. It's not a statistic. Does that make sense?
Yeah, that makes much sense. Yeah.
Okay. So in other words, whether the output of the statistical functional is random or not is depending on the input being random or not. So here the empirical CDF is of course a random function because it's from a random sample x1 to xn. Just as a recap, in case not everybody remembered as well. So if we evaluate this, f and hat at any value, small x, it's basically the average of these indicator functions, indicator whether each xi is less or equal than this x, right? It's this proportion. That's what we define as the empirical CDF. And you can see that because x1 to xn are random, then this f and hat, no matter which fixed x you evaluate it at, it's a random value. So it is random. So that's why as a random function here, you input it into the functional t, the output, which is a statistic or parameter estimate, is still random. So the random nature will be kept. Okay, so that's a functional. And then the next question we want to talk about is what is, so how can we talk about, the next thing we want to talk about is what we call this, the expectation functional. Okay, so by the name, you can know that it's about some sort of expectation. Okay, so what we can say is that we have, let's say we have this function g, okay, that maps from an m-dimensional space to the real line. And also, let's say that we have y1 to y from a, so therefore, expectation functional takes this form. TF is defined as the expectation of g y1 to ym, and the expectations taken under for all the y1 to ym, and because they all follow distribution f, so I keep the f here as a subscript of expectation symbol. So this way I can make sure, yeah, it's a function of f, and f appears also on the right. Otherwise, it doesn't make any sense. Okay, so when I write it this way, I'm implying that y1 to ym are IID following f. That's what this notation implies. Okay, so one question we wonder is that, is this g function symmetric? Which means that if I permute its argument, does the g function have the same value? Actually, not necessarily, because this g function could be any function. So let me just give you one example. Okay, if I define g, y1, y2, let's say m equals 2, and I have only two arguments, if I define it as y1 over y2 in this way, then clearly this g is not symmetric, right? Because if you swap them, then g, y2, y1 become y2 over y1, and that's not equal to y1 over y2. So g is not necessarily symmetric. However, because of IID property, we actually can have symmetric property for the expectation. So what I mean is that even if we don't have g y1 y2 equals g y2 y1, but we do have the expectation of g y1 y2 equals expectation of g y2 y1. So with the expectation, things are changed. Why is that? The reason is that y1 y2 and y2 y1 are following the same joint distribution, because I can say y1 y2 has the same distribution as y2 y1, because y1 y2 are IID because of this property. So no matter if you swap them, you still have independence, and marginally y1 and y2 have the same distribution. So therefore y1 y2 and y2 y1 have the same joint distribution. So therefore their expectation after g transformation will be the same. Does that make sense to everybody? Okay, sounds good. So therefore, even though my g may not be symmetric, I can create a symmetric version of g as follows. So I can make g symmetric by, I define g star, okay? So in my definition of g star, I would define it as, say, the m argument. I just use lowercase to refer to it, y1 to ym. It's m arguments. I define it as the average of all possible G ordering. So, if I permute the M arguments, I have M factorial possible permutations, okay? And I would just take the summation of all pi. So we often use pi as a permutation. And then I will have G of Y pi 1 to Y pi M. So what does that mean? So let's say pi will map, it's a permutation. So it will shuffle the order of 1 to M in a way. So therefore, say pi 1 could be 2, pi n could be 4, etc. So it's just another way of shuffling the order 1 to M, but each 1 to M will only be mapped to one number. And so there will be no repetition after the permutation. So with this permutation, you see, I can just enumerate all possibilities and evaluate them at the function G, and then I take the average of G. So with this definition, G star would by nature symmetric for its M arguments. So you can easily see that by the definition, then G star Y1 to Ym would be equal to G star of any permutation pi, Y pi 1 to Y pi M. So it's because if you put Y pi 1 to Y pi M to here in the definition, the right-hand side will stay the same. Okay, so why does this matter? To make G with a symmetric version. The reason is that even though clearly G does not, so let's say Y1 to Ym, does not equal to or may not be equal to G star Y1 to Ym. That's possible if G is not symmetric. But on the expectation level, the two things are the same. The expectation of G with the capital Y1 to Ym following F would equal to the expectation of G star Y1 to Ym. And we only care about expectation because that's how we define the TF, right? So this is what we defined as the TF. So therefore, after this argument, the conclusion is that for the expectation functional, we can assume G as symmetric, as a symmetric function without loss of generality. The reason is we can always find a G star so that they share the same expectation. So that's why we can safely assume that in the expectation functional, G is symmetric without loss of generality. Okay, so we can assume without loss of generality that G is symmetric about its M arguments in the definition of TF. And this argument will make our following discussion simpler. Okay, so does that convince everyone? So even if G is not symmetric, we can create G star to be symmetric, and they share the same expectation function. Okay, so that's the starting point. Okay, so now let's look at what we say the starting point for doing the plugin. So let's say that we have an expectation functional as our parameter of interest. Okay, so let's say theta is TF and it's an expectation functional. So we write as EF of G y1 to yn. Okay, so in what case, let me ask you a question. So which special examples can you think of this case? Mean, right? Median, oh, sorry, not median, mean, variance. These are all special cases of this expectation functional. So for example, in the mean, what is the mean? So if we have mu, right, then we can just write it as expectation of fy. So in this case, m equals 1 and g of y is just y. It's just the identity function. That's the special case. Okay, so this is just one example. And sometimes, you know, some special functional may need to be defined by two IIDs. So when m equals 2, two IIDs from the F distribution, and we can see that. But this mean is just enough to be defined by one random variable from the distribution and expectation. Okay, so that's the parameter of interest. Now let's do plugging. Okay, and to plug in Fn hat sample empirical CDF. And we actually give it a name. It's actually called a V statistic. And this V comes from a statistician who was one of the founders of the discipline, von Mises, and he's right. So that's why we have this V coming from the last name. The V statistic is exactly here, just denoted by VM. Okay, is exactly the expectation functional evaluated at empirical CDF. So writing things correspondingly one by one, we can see that this is expectation under the empirical CDF Fn hat. Still G function. Okay, so even though we can still use this y1 to ym for notation consistency, but we must bear in mind that here the y1 to ym in our case here are following Fn hat instead of F. Okay, now let me ask you, what does it mean that they are IID following Fn hat? In practice, what does Fn hat mean? It's the empirical CDF of your sample. So let's say that this Fn hat is from my sample x1 to xn, okay, which are themselves IID from F. So given the sample x1 to xn that defines Fn hat, what does it mean that y1 to ym are IID from this Fn hat? Or maybe think about what does Fn hat mean in a concrete way. So if you remember, and if you look at this formula right here, you can see that Fn hat essentially places a point, probability point max 1 over n at each of my x1 to xn. They share equal probabilities, right? So then to sample from this discrete distribution, which we call Fn hat, to draw y1 to ym, I'm basically drawing from x1 to xn with replacement. That's what I mean. So this part is essentially saying that y1 to ym are independently sampled with replacement from the set x1 to xn. That's what it means. So therefore, we would know how many possibilities are there, right? So each yi can be one of x1 to xn. And they are sampled independently of each other. So therefore, how many possibilities can I have for this y1 to ym? Each one has n possibilities from x1 to xn. So, and they're independent, so I multiply them. So the possibility is actually n to the power m. I can have so many possibilities for my y1 to ym. So I divide by that total number of possibilities and I enumerate all possibilities. So in other words, y1 could be any of x1 to xn, y2 could be any of x1 to xn, so are ym. So therefore, I would have m sums, okay? And I just denote each one by index I1 to IM. So I1 is the pick for y1. It can go from 1 to n. And so in that case, I would pick xi1 as my y1. Okay, and so for yn, I would pick xim as my yn, and im can go from 1 to n. So I'm just writing out all the possibilities that my y1 and ym can take from this empirical CDF. Does that make sense? This is what we call V statistic, which is the direct plug-in version of the expectation functional. Okay, so now if we're fine with this, then let's make things simpler. Go back to the simple expectation functional when m equals 1. We have only one argument. So when m equals 1, then it's actually pretty easy because you see Vm is just reduced to 1 over m equals 1. And we are reducing the m sums into one sum. Okay, because we only have one I1. I don't need the 1 for the specification. I just say I from 1 to n, g, xi, right? So in this case, you see, this is the estimator. I'm basically using my sample, x1 to xn, to, this will estimates the expectation under f of gy. That's it. So I'm using my sample as the sample estimate, right? This is sample mean to estimate the population expectation. So this is something very natural. And very obviously, you see the expectation of the Vn statistic here would be equal to my statistical functional, the parameter of my interest. So they are all the same thing. So in this case, EVN will clearly equal to TF and equal to the parameter of interest. Okay, so this is very good, right? When m equals 1, we don't have any issue. But when m equals 2, so when m is greater than 1, we do have some repetition issue. Let's look at one example. Okay, so in this example, let's say m equals to 2. And we define the g function with 2 arguments now as the absolute difference of its 2 arguments. So with this g, then let's see what's the corresponding statistical functional. TF will be the expectation under f of absolute y1 minus y2 difference, and y1, y2 follow f. Okay, so how does this work, right? So let's say we have a random sample, x1 to xn. The sample is IID from f, and we want to do a plug-in estimator for TF, the V statistic. So here, the V statistic, following this formula, it will actually be equal to 1 over n squared, I1 from 1 to n, I2 from 1 to n, and it will be, this is the G function, xi1 minus xi2. Okay. And think about what possibilities this can take. So you can see that for how many cases are x1, xi1, and xi2 not equal to each other? How many cases are there? So it will be the cases when, so I'm just from my, from my n, x1 to xn, those n items, I'm going to pick two different ones. And here, xi1 and xi2, I can consider the two orders. So for example, xi1 is x1, xi2 is x2, versus xi1 is x2 and xi2 is x1. I consider them to be two cases instead of one case. So therefore, you see, the possibilities is actually n times n minus 1. So for those cases, I have them different. Okay, so let me just say that in this summation, for n times n minus 1 cases, xi1 doesn't equal to xi2. Okay, but for the remaining n cases, xi1 equals xi2. So when we talk about this V statistic and consider its expectation, we need to separate those two cases. So then when we take expectation of Vn, we know that when expectation enters the summation, we are going to have n times n minus 1 cases when they are different. And when they are different, they share the same expectation. So therefore, I can just write it for simplicity. It's x1 minus x2 as representative. And for the remaining n cases, I can write just x1 minus x1 as a representative. So clearly, for the n cases here, the expectation will be 0. Because the itself minus itself give me 0. So then I'm only left with the former n times n minus 1 cases, and I can cancel the n. So I'm left with n minus 1 over n times expectation of x1 minus x2. And because x1, x2 follows what? They follow F distribution. So that's why this is exactly TF. So you see, I have a bias here. So the V statistic no longer have its expectation equal to TF. So this tells me Vn is biased. Okay. So even though we can say the bias will go down to 0 as n goes to infinity, because n times n over n minus 1 over n is convergent to 1. But without talking about asymptotics, just with a finite n, clearly Vn is a biased statistic. Okay, do we have a question for this? All right. If not, then let's continue. How do we correct for the bias? To do that, we need to think about the source of this bias. The source is actually from the fact that when we just do this plugin to replace f by the fn hat, when we sample y1 to ym from fn hat, we may draw the same one of the x1 to xn, the sum of the original sample for more than once. So in other words, it was the repetition, like here, right? Same x1 was sampled for twice, that caused the issue. So if we restrict ourselves, so in this definition, to force that here the I1 to IM, these M indices are not equal to each other. If we force that, then we can make sure there will be no repetition in the M arguments of G. So we can reduce the bias. We can remove the bias. So that's exactly the motivation to develop the U statistic from the V statistic. So U statistic is defined as the unbiased version. So following the VN definition, just look at it again. It's considering for Y1 to Yn, the V statistic is considering all n to the power n possibilities for picking from X1 to Xn without worrying about the repetition. But here we want to just get non-repetitive elements of X1 to Xn. So therefore, in the definition of UN, we do not consider n to the power n possibilities. Instead, we consider only n choose m possibilities. This can make sure that the chosen n items are not repetitive. They are different elements from in the X1 to Xn set. Okay, so with this, then let's consider what are allowed for I1 to IM, the indices. Okay, so still I'm going to put it here. The sampled ones I call XI1 to XIM. And also, you know, this n choose m doesn't consider orders. So basically, let's say if m equals 2, and picking x1, x2, and x2, x1 are considered to be the same. So order is not preserved. So therefore, I need to enforce that in my I1 to IM possibilities that I have an order. I1 is less than I2, less than IM, and they are both between 1 and m. Okay, so that's how I define the U statistic. So in other words, when we draw sample for Y1 to Ym from X1 to Xn, we only restrict ourselves to the non-repetitive elements of X1 to Xn. Okay, so that's why we are left with n choose m possibilities. And therefore, we can easily show that in this case, expectation of UM, if you make the expectation inside the summation, then for each expectation of G, XI1 to XIM, because they are not equal to each other, they are equal to TF. So I would be able to show that, and inside the sum, there are n choose m possible sums, and they all have the same expectation. So I cancel with this division. I have that equal to TF. So that's why we have the unbiased. Because of this definition. So to just do a quick recap, like we're saying that if you want to have an unbiased estimator for that expectation functional, you cannot simply do plug-in by replacing the f by fn hat as in the V statistic, because that will introduce some repetition. And I think to help you better understand the next topic after finishing this part will be bootstrap. So essentially, the V statistic was like bootstrap. You are doing sample with replacement, so you may have repetitive data points, and that will cause issues with the bias. But in the U statistic, when you draw a sample of M from your original sample of size N, you only sample non-repetitive elements. Okay, and of course, you see the U statistic is only feasible when its definition, the number of arguments in G function, the M, is less than N. If NM is greater than N, this is not possible. In other words, in your definition of the statistical functional, the number of random variables in your G function, so here in the definition, Y1 to Ym, you cannot have this M greater than your sample size in the U statistic, otherwise it will not be existent. Okay, So now let's look at one concrete example of a use statistic. And that's what we call the Wilcoxon. This is called a paired Wilcoxon test. Okay, so let's look at that. So paired Wilcoxon statistic. Look at this as a concrete example. So let's say our sample is paired. Okay, so x1, y1, 2xn, yn. They are paired. And of course, we assume they are paired IID. So now let's define Zi as just yi minus xi. So the Wilcoxon test, the pair test, is still concerning whether the x1 to xn and y1 to ym would actually follow the same distribution, actually come from the same distribution, and they're paired. So if they do, right, so then it will be natural to think this Zi would be symmetric about 0, half of a chance taking negative values, half of a chance taking positive values. And that's the thing we want to test, whether that's the case. Okay, so we want to see, does Z1 to Zn follow a distribution, an IID F distribution? Okay, does this F distribution have mean, or is this F, okay, let's see this. Is this F symmetric about 0? That's the question we want to ask. Or maybe it's better to say that, is this F have a median 0? Maybe that's a better way of saying it. Yeah, has median 0. Okay. So to answer this question, we would like to say that, so to answer this question, the Wilcoxon is called the Wilcoxon signed rank statistic. So the signed rank statistic is as follows. So first of all, we actually took the absolute values of Z1 to Zn and then ranked them, okay, from the smallest to the largest. So what we mean is that, so let W1 to Wn be a permutation of Z1 to Zn such that W1's absolute value is the smallest and Wn's absolute value is the largest. So you can think of W1, Wn just being an ordering of Z1 to Zn such that they are ordered by the absolute value from the smallest to the largest. Okay, then what's the signed rank statistic? Right, so what would you imagine if this hypothesis is true? That is, this difference Z1 to Zn have median 0, the distribution has median 0. That means the sign, right, should be independent of the absolute value. We can have large absolute value with positive and negatives, and also small values with positive and negatives. That's what we have. So here the rank sign statistic is defined as Rn, which is defined as the summation j from 1 to n. J here times the indicator function that Wj is positive. Then what would you imagine? So if Wj is positive for the large j's, right? Large j means having large absolute values. So if the large absolute values tend to be positive, then we would say the null hypothesis is unlikely to be true. And if we have this sign independent of the rank, right? So we may have this indicator function equal to 1 for a random number of j's, then you wouldn't expect this to be that large. On the other, the Rn to be that large. On the other hand, if you have all the positive wj's in the lower end of the absolute value, then the Rn will be small. And that's another suggestion the null hypothesis may be validated. So that will tell me that intuitively, a too large or too small Rn will suggest violation of the null, while the middle value of Rn will suggest a null likelihood. So that's the intuition we have here. But how can we use our use statistic to help explain this? So let's think about this formula, and we can have an interesting intuition from it. So let me try to finish this example, and then we will end this class because we need to make up some missing time from last lecture. All right, so let's think about what does this order tell us. And we see that the order tells us that Wi is less or equal than Wj, right? If I is less than j. So we have this order. And so therefore, if I is before j, what can tell me? So Wi plus Wj is equal to 0 for what? If and only if Wj is positive, right? So the sum is positive only when the larger absolute value is from a positive. Otherwise, it couldn't be positive, right? This will make sense. So you see, if Wj is negative, no matter what sign Wi has, the sum cannot be positive. So this equivalence is very important. So because you see in this Rm, you see I can write it as what? I have j copies of indicator Wj greater than 0. And I can pair Wj up with W1, W2, and W3, right? So you can see that I can pair them up. And so every time when W1 plus Wj is greater than 0, based on this argument, is equivalent to Wj is greater than 0. And also W2 plus Wj greater than 0 is equivalent to Wj greater than 0. And finally, Wj plus Wj greater than 0 is equivalent to Wj greater than 0. So therefore, I can write in the summation as I let I go from 1 to j, and I change this to indicator Wi plus Wj greater than 0. Okay, so I can do it this way. And then you see, I'm taking this summation can go one step further. So with this sum, now you see, I'm doing this double loop, j from 1 to n, I from 1 to j. And I go through every Wj and every Wi, right? So therefore, you see, I'm going through all the Wi and all the W1 to Wn using this double loop. And therefore, it's actually equal to the unpermuted version of W1 to Wn. That's Z1 to Zn. So in other words, since I'm going through everything, I can replace Wi, Wj by Z1, by Zi, Zj without changing anything. Okay, so that's the key. So you see, I can write this as j from 1 to m, I from 1 to j, indicator Zi plus Zj greater than 0. Okay, so I'm here. And finally, you see, this is what? This is just a little more than our use statistic. In our use statistic, if you think about it, I and j cannot be equal. So therefore, if it's a U statistic, I can only go from 1 to j minus 1. It cannot be equal to j. So we are having some additional things here, but that's fine. We can just separate that. So I'm just going to continue from here. So you see that this Rm is equal to what? I have just I less than I greater or equal than 1 less than j greater or equal than m, indicator zi plus zj greater than 0. That's what I have. And then I will have a remainder, right? The remainder is just j from 1 to n, indicator zj greater than 0. So that's my signed rank statistic. And then finally, what's the connection with the U statistic? We just need to divide this by n choose 2. That's our U statistic. So divide by n choose 2. Okay, then what would I have? I would have Rn divided by n choose 2 equals to, this becomes the U statistic, Un, plus, here is the summation j from 1 to n, izj greater than 0, divided by n choose 2. So in the numerator here, it's at most n. And what's n choose 2? It's actually on the order of n squared. So therefore, you see this divided by n, at most n divided by n squared will give me an order of 1 over n. So therefore, I can write this as um plus big OP in probability 1 over n. All right, so why do I need this result? The result just tells me that for the sign rank statistic, if I standardize it by n choose 2, it's basically the U statistic for which we are going to derive asymptotic distribution in the next lecture, plus a remainder that will diminish to 0 in probability. So therefore, the U statistic theory will be very useful. This is one application. With that, you can obtain the asymptotic distribution for the Wilcoxon signed rank statistic to derive its null distribution. So this is just one application to make some connection to the U statistic. So we'll stop here for today. And starting with next lecture, we are going to talk about how can we derive a general asymptotic distribution for this U statistic, which can represent a big family of unbiased statistics, unbiased estimators. Okay, any questions before we end here? If not, so then hopefully I'll see you on Wednesday. Bye. Oh, actually, yes, and we are recording. Yeah, I was so scared. I forgot that. All right, bye.
Thank you.
Bye.